let's talk about more complex sets. And one way to get more complex sets is to take sets that you already have and perform set operations on them. So let's look at the set operation. So we have complement, so set operations. Okay, so we have complement, union, intersection. Okay, and languages are sets, so we can do any set operations that we can do on sets, we can do on languages. And we saw two other operations we do on languages, which is this thing called concatenation and Kleene star. Okay, so we have concatenation and Kleene star. Okay, so these are set operations. So let's see. Okay, so here's a language, okay, and here's a machine that solves that problem, that solves that language. So what about the complement? So L1 complement. Okay, now we can describe those strings that do not have a zero. Strings with no zero. And L2 complement. L2 complement equals strings with ending that do not end in 1. Okay. So doing the complement is especially easy. So I'm going to pause the video for a few seconds, pause the video, and figure out what machines solve the complement. So 1, 2, 3, 4, 5. Let's do it. Okay. I'm going to take the same automaton, the same machine, Q0, Q1, okay, which goes 1, 0, 0, 1. Okay. Now, let's see. To solve this problem, if I said yes here, I should say no here, because a string is in this set if it was not in that set. And if I said no here, I should say yes here. So all I have to do is switch the yes and no states. So boom, switch the yes and no states. So this becomes my new yes state. Done. We've implemented the complement. So if you give me any language and you show me a machine that solves that language, I can solve the complement with almost no effort. I just flip the yes and no states. Okay. So complement, if a language can be solved, if a problem can be solved by a finite automaton, the complement can be solved. Okay. Let's talk about, so here are two languages, L1 and L2, and here are finite state machines that solve L1 and L2. Can I solve the intersection? Can I solve the union? Okay, so can we all solve the union, L1 union L2? What about L1 intersection L2? Okay, so now we're getting into some more sophisticated methods for designing automata. Okay, and I'm going to show you a nice trick that's called product states. So you don't need to reason about what the union is or what the intersection is. I'm going to show you that we can solve the union directly using the two machines that solve the individual languages. Okay. So we can solve, so let's name these machines, M1 and M2. So we can solve the union, L1 union L2, and the intersection, L1 intersection L2, without reasoning about the languages, by just using the machines, by just using the machines M1 and M2, okay, and then constructing a new machine to solve the problems that we're interested in, and constructing a new machine, let's call it M. Okay, directly constructing a new machine M without even looking at the languages. All I need to know is that M1 solves L1 and M2 solves L2. Now I'm going to show you how to construct M to solve the union. The same method works to solve the intersection. Okay. The idea is simulation. I'm going to simulate the running of M1 and M2 in a single machine M. So the idea, simulate the running of M1 and M2, using M. Okay. So let me tell you what I mean by simulate the running of M1 and M2. So if I'm going to simulate the running of M1 and M2, I must certainly be able to simulate the start configuration. So if I'm starting on a string, let's imagine that I start on a string. Okay, where does M1 start? M1 starts, okay, so now I'm going to be a little more careful. I can label the states any way I want. So let me label these states, S0 and S1. S0 and S1. It's the same automaton. I just relabeled the states. But I don't want to have multiple states that are labeled Q0 and Q1. Okay, so to remove confusion. Okay, so if I'm thinking of running both M1 and M2 on a string, where do I start? Well, I start with M1 in state Q0 and M2 in state S0. So I'm going to simulate this process. So I'm going to imagine a start state, which is, Q0, S0. You can think of this as saying, that says that M1 is in Q0 and M2 is in S0. Okay. And this is where this machine that simulates M1 and M2 starts, because M1 is in Q0, M2 is in S0. Now let's see what happens, okay, when I get a 0. Okay, so if I get a 0, okay, what happens to M1? M1 transitions to Q1. What happens to M2? M2 stays in S0. Okay, so if I get a 0, okay, M1 transitions to Q1 and M2 stays in S0. So I'm gonna say that my machine that's simulating them both, okay, transitions to the state Q1 for M1 and S0 for M2. So that's the way we read this state. It's kind of encoding that M1 is in Q1 and M2 is in S0. Okay. What happens in this? What happens, from the beginning if I get a 1? If I get a 1, well, M1 stays in Q0 and M2 goes to S1. So if I get a 1, okay, M1 stays in Q0 and M2 goes to S1. So I'll transition to a state that represents that. Okay, Q0, S1. M1 is in Q0, M2 is in S1. Okay. All right. Okay, good. So that's what happens at the beginning. Okay. But now let's think. So I've told you what happens from the starting state. Okay. Now what happens from this state? Let's think about what this state is. This state says that, M1 is in Q1 and M2 is in S0. So you're in Q1 and S0. What happens if you see a 0? M1 stays in Q1, okay, and M2 stays in S0. So if you see a 0, M1 stays in Q1 and M2 stays in S0. So if you see a 0 in this state, which represents, M1 is in Q1 and M2 is in S0. If you see a 0, M1 stays in Q1 and M2 stays in S0. What about in this state if you see a 0? So you're in Q0 and S1. If you see a 0, okay, you transition to Q1, S0. Okay, so if you see a 0, you transition to Q1, and this guy transitions to S0. Q1, S0. This is what happens in this state if you see a 0. Okay, so we have Q0, S1. When you see a 0, transitions to Q1, S0. So this is a 0 here. Okay? All right. Now, in this state, Q1, S0, so Q1, S0, what happens if you see a 1? You stay in Q1 and you transition to S1. So Q1, S0, if you see a 1, you stay in Q1. You stay in Q1 and M2 transitions to S1 if you see a 1. Okay. What happens in this state if you see a 1? So you're in Q0 and S1 and you see a 1. You stay in Q0, S1. You stay in Q0, S1. Okay, so this state, if you see a 1, you stay, M1 stays in Q0 and M2 moves into S1. Okay. So this is what it means for M to simulate the running of both M1 and M2. Its states capture both the state, capture the states of both M1 and M2, and it makes the transition that reflects the actual transition that those two machines make. Okay. Is this automaton done? Not yet, because I need to tell you in this state of my new machine M, okay, what happens when you see a 0 and what happens when you see a 1. So you're in Q1, S1. You're in Q1, S1. Okay, when you see a 1, you stay there. 1 keeps you in Q1, 1 keeps you in S1. When you see a 1, you stay there. What happens when you see a 0? Well, Q1 stays there, but S1 transitions to S0. So you transition to Q1, S0. So if you see a 0, you transition to Q1, S0. Okay. So there's an interesting automaton. Okay, I claim that this automaton M simulates the running of M1 and M2 simultaneously. Now let's see that in action. Okay, so let's see that in action. So let's consider the string, let's say 0, 0, 1, 0. Okay. So what happens with M1? So let's talk about M1. So we start in state Q0, okay, and we're processing 0, 0, 1, 0, 0, 0, 1, 0. Okay. With respect to M1, so the machine M1 under the machine M1, the state Q0 when you see 0 is going to transition to Q1. So you've processed the first bit, and now you're processing 0, 1, 0. Okay, so you've gone to Q1. You're in Q0, you see 0. You go to Q1. Okay, you're in Q1, you see 0. You stay in Q1. You're in Q1. Okay, so you stay in Q1 and you've now processed both zeros. Okay, you're in Q1, now you process the 1. Okay, so you stay in Q1. And you're ready to process the 0. So this is all M1. This is M1. Okay, and one final processing step. You process a 0, you process the 0, you stay in Q1. And now you're done. Okay, and M1 would say yes. Okay, let's look at what happens in M2. So you're processing this string. So you start in state S0, and you're processing the string 0, 0, 1, 0. Okay. You process the 0, so the 0 keeps you in S0. So under M2, you stay in S0, you've processed the 0, and you have remaining 0, 1, 0. So you process another 0, you stay in S0. You stay in S0. Okay, so you process 2 zeros. Now you have 1 0 left to process. So you process the 1. So it transitions you to S1. And you process 0, 0, 1, and you have a 0 to process. And one final bit, you're in S1, you process the 1. Okay, you're in S1, you process the, you're in S1, you process the 0, takes you back to S0. S0, and you've now processed all the bits, and you're done. Okay, so here, M1 says yes. Okay, M2 says no. Okay. Now, quick exercise for you. Okay, do it before I do it. Well, I'll pause the video. Okay, do the trace of the computation for M. So let's call this guy M. This is M. Okay. So let's do it. The start state is Q0, S0. So we have Q0, S0. Okay. And we have all the bits to be processed. 0, 0, 1, 0. We process the first 0. That takes us to Q1, S0. And we process the first 0. And we have 0, 1, 0 left. So Q0, S0, the first 0 takes us to Q1, S0. We process the next 0. And the next 0 keeps us in that state. So we're in Q1, S0. We process the second 0. Okay, and we have 1 0 left to process. Okay, so we process the 1 from this state Q1 S0. So we process the 1, and the 1 takes us to Q1 S1. And we process 0 0 1, and we still have the 0 left to process. Okay, by the way, this is M under the influence of M, under the influence of M, under the influence of M. So I'll draw a line here, and a line here. Okay. And now we process the final bit. So under the influence of M, we are in state Q1 S1, and we process the 0. So that takes us back to Q1 S0. And we have no more bits to process. Okay, so you see how convenient this sort of way of representing the configuration of the computation and this whole computation trace is. Okay, now what I want to show you. Let's track the progress of M1. So it starts in Q0, then it goes Q1, 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 Q1. But look at what M did. Starts in Q0 and then went Q1, 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 Q1. Let's track the process of M2. It starts in state S0, then it goes S0, 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 S1, S0. And look, S0, 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 S1, S0. M is simultaneously running both M1 and M2. And at any stage in this guy's computation, we can look at what my state is and we will be able to figure out where's M1 and where's M2. Okay, now, let's say we want to do the union. So if we want to do the union, okay, so you should say yes if, either of these guys says yes. That's what the union means, strings that are in the union of these. Okay, so you combine all the strings. So if we wanted to do the union, M1 says yes, M2 says no, you should say yes. Okay, so for union, M should say yes. For intersection, M should say no. Intersection means that both of them must say yes. So you must be in both sets. Okay. Now, how would we implement that? Okay. So the only thing that is missing from my automaton is what are the accept states, what are the yes states, and what are the no states. Okay. It's the only thing that's missing. So what are we going to do? If we want to do the union, okay, the accept states should be either, so you can look at the individual states, okay, and if either of those individual states is an accept state for the corresponding automaton, okay, it should be an accept state of the union automaton. So for union, yes state are states which are yes for M1 or M2. Intersection, yes states are yes states are states which are yes for M2, for M1 and M2. So if I'm doing the union, I set the yes states as the or. If I'm doing the intersection, I set the yes states as the and. So let's look at that in practice. So if I want to do the union, Q0, S0, both are no states. So this is a no state. Okay. Q1, S0. Okay. Q1, S0. Well, it's a yes state for M1. So this becomes a yes state if I'm doing the union. Q0, S1. So Q0, S1. Well, S1 is a yes state. So this becomes a yes state if I'm doing the union. Okay. And then Q1, S1. Well, Q1, S1 is a yes state for both. So this becomes a yes state if I'm doing the union. And there I have finally specified my automaton M that does the union of these two languages. Okay, now you should feel comfortable that, no matter what automata you give me, I can do the union using this process. These states in here are called product states. For the obvious pictorial reason that it looks like I'm taking a product of the states. How many states are there in my union automaton? The product of the number of states in here times the number of states in here. So here I have 2, here I have 2, 2 times 2, 4. That's why I have 4 states in here. Another reason why we call them product states. Okay. Now let's say I was doing the intersection. Okay, so let's say I'm doing the intersection. So this is the union automaton that implements the union of the languages. If I'm doing the intersection, okay, then my yes states must be yes states for both automata. Okay, and the only state that's a yes state for both automata is Q1, S1. So that's Q1, S1. There is the automaton that does the intersection. That's it. Okay, so the idea is I'm going to create an automaton that simulates both together. And then at the end, decide which are yes states and which are no states, depending on whether I want to do the union or the intersection. Wow! So complement, no problem. Union, intersection, no problem. Okay, now complement was easy. I just flipped yes and no. But union and intersection are a little bit harder because I have to sort of build this simulating automaton and then, decide which are the yes and no states based on which are the yes and no states of my original automaton. So let's summarize.